This is section 2.2, separable differential equations. So the first problem is if the equation given is separable. If it is, we're going to find the explicit solution. Well, the given equation is dy dx equals to 18x secant of y. And yes, this equation is separable because we can put all the y's together on a side and all the x's together on the other side. So that is, we can rewrite this equation as dy divided by secant of y equals to 18x dx. Then we know that secant, or 1 over secant, is the same as cosine of y dy equals to 18x dx. And now we can find or apply the integral on both sides, right? So the integral of cosine of y is sine of y equals to the integral of 18x is 9x squared, right? Plus some constant, right? Now, this solution is implicit because y is not isolated. We need to find the explicit solution. Then we have to isolate y. We need to leave y alone. So we can do is to isolate y by y as sine inverse of 9x squared plus c. And then we're done. This is the explicit solution as y is isolated. The second example is that given equation a separable equation. If it is, can we solve it? Well, this equation is not separable because we cannot. It's not separable, as we cannot separate the variables. For example, if in our attempt to separate variables, we rewrite it like this, there is no way that we can separate the x's and the y's. So it's not separable, so it cannot be solved using the separable equation method. Example 3. Is the equation separable? If it is, find the solution. Well, let's see. If dy dx equals 2, I believe that we can factor on the top of the right x. So we have 1 minus y over x is secant plus 1. Then we can rewrite the equation as dy over 1 minus y equals to x divided by x to the second plus 1 dx. As you can see, all the x's are on a side and all the y's are on the other side. So yes, it is separable. Okay. Now, what next? Now we need to move to find the integral to find the solution of the equation. Then, how can we do that? Well, we have an integral in yellow and we have an integral in blue. Let's solve these two integrals in a separate way. So, the integral of dy over 1 minus y, here we can use substitution. We can say that u is 1 minus y. Then du is equal to negative dy. Then dy is equal to negative du. And then we replace this information in the given integral. We're going to have the integral of negative du over u, right? Which is negative integral of du over u, and the integral of du over u is negative ln of absolute value of u, which is the same as negative ln of 1 minus u, replacing u by 1 minus u. And then all this belongs to the yellow integral. Let's now do the blue. The integral of x divided by x to the second plus 1 dx. Then, here we can apply substitution again. We may say that u is x to the second plus 1. Then du is 2x dx. Then dx is du over 2x. Then the integral now becomes the integral of x divided by u times du over 2x. The x's cancel. Then we can write it as 1/2 the integral of 1 over u du, or simply du divided by u. And then this integral is kind of the same as the previous ln of absolute value of u, but now u is x to the second plus 1. Then, so all this belongs to the blue integral. Okay, so now our integral is then the yellow part is negative ln of absolute value of 1 minus y, and then the blue is 1/2 of ln of. Here we can get rid of the absolute value because this inside, I mean the argument of this log is going to be positive always, plus c, right? Don't forget the c. So this solution is implicit because y is not isolated. Let's try to isolate y. Well, if we exponentiate on both sides, exponentiate both sides, we have uh, 1 minus u to -1, assuming that the absolute value is positive, equals to x to the second plus 1 to 1/2 times e to the c. And then again, I'm going to call this as c. It's a constant. Could be c1, but I'm going to call it c. So we have 1 over 1 minus y equals to c times x to the second plus 1 to 1/2. And then now we need to isolate y. Then this expression is equivalent to 1 over c x to the second plus 1 to 1/2 is equal to 1 minus y. Therefore, isolating y is equal to 1 minus 1 over c x to the second plus 1 to 1/2. And then this is an explicit solution because y is isolated. Example 4. Example 4 is an example of an initial value problem. What is an initial value problem? Well, an initial value problem is or consists of a differential equation and a condition. So recall this condition is equivalent to the point pi comma e. Pi comma e. X is pi and y is e. So we have cosine square of x times y prime equals to y ln of y. That's the given differential equation. So we should try to using separable method isolate or try to solve the equation. So recall y prime is the same as dy dx, derivative of y with respect to x, equals y ln of y. And then we can separate variables. We can say that this is equivalent to dy over y ln of y equals to dx over cosine square of x. And then recall that on the right, we can write cosine square as secant square of x dx. Then now integrate, find the integral. So the integral of dy over y ln of y, it is ln of absolute value of ln of y. The integral of secant square, we know is tangent of x plus c. So this is our implicit solution. So now a condition is given. A condition is given. So we replace the condition in the solution we found. The condition is y of pi is e. Remember, this is equivalent to pi comma e. Okay, if we replace this point in the equation, we have ln of absolute value of ln of e equals to tangent of pi plus c. So ln of e is 1. ln of 1 is 0. And tangent of pi is 0 plus c. Therefore, c is 0. So our equation is ln of absolute value of ln of y equals tangent of x. And that's the solution. Implicit, by the way. So you want to find the explicit solution, then we have to exponentiate on both sides. So we have e to ln of y. So what do we have? ln of y equals to e tangent of x. Still y is not isolated. So trying to isolate y, we need to exponentiate again. So we're going to have what? E, we're going to have y, because e to ln of y is simply y, equals to e tangent of x. Example 5. This is another initial value problem. And then the only method we have seen so far is separable equations, separable method to solve differential equations. So this condition is equivalent to the point 1 comma negative 5. So can we separate? Yes, we can separate variables because we can write the equation as dy dx equals to y times 10x to the 6 minus 1. That is a separable equation. Then we can separate it variables and then write it as dy over y equals to 10x to the 6 minus 1 dx. Apply an integral on both sides. And the integral of dy over y is ln of absolute value of y. The integral of 10x to the 6 is 10x to the 7 over 7. The integral of 1 is negative x plus c. And then we can try to isolate y, because this solution, in this solution, y is not isolated, it's implicit, and we can try to isolate y. We need to exponentiate both sides. So we have simply assuming that c is not a non-zero constant, we have e to 10 over 7x to 7 minus x plus c. And then this is equivalent to e to 10 over 7x to the 7 minus x times e to the c. And then I can call this c again, or any other letter, and then write the solution like this. Now, remember, this is an initial value problem. A condition is given, right? Condition is given. So this condition is given. So we replace this in the solution we found. We have negative 5 equals to c e to 10 over 7 10 over 7 times 1 minus 1. We have negative 5 equals c. 10 over 7 times 1 is 10 over 7. 10 over 7 minus 1 is the same as e to 3 over 7. So from here we conclude that c is negative 5 e to negative 3 over 7, right? We isolate c. So our equation is going to be y equals to c. So what is c? Negative 5 e to negative 3 over 7 times e to 10 over 7 x to 7 minus x. Then it is equivalent to negative 5 e to 10 over 7 x to the 7 minus x minus 3 over 7, combining all the exponentials together. And this concludes the solution of the initial value problem.